Welcome, everybody. Just wanted to wait a few minutes before to allow everybody to join in. So we'll just wait a few minutes. Just gonna mute my phone. Okay, I think we're probably good to get started. Just want to welcome everybody and thank you for all joining us today on our webinar on asset performance management. This webinar will be recorded and will be posted on our YouTube channel, along with all of our other webinars and videos that we've created to this date. Please check it out when you get a chance. And now I'll do the introductions. So I'm Danny Haskell, president of NeoMatrix. I have here with me Chris VanRemoortel, who's our solutions architect. And also we have Pedro Espinosa, who's our automation engineer too with us. We are a software services company, systems integration for plant automation services, MES solutions, and enterprise integration. We were recently acquired in March of 2025 by Ondex Automation, which provides additional capabilities that we didn't have before. Live Automation does controls engineering, but they also do custom automated design and build of equipment, including robotics and vision. ACI designs and builds UL panel shop and also has a pretty significant electrical install team. For our agenda today, Pedro is going to walk us through what is APM and why it matters. And then we have a live demo of a standard NeoMatrix APM solution. And then Chris is going to go a deep dive in a case study of an APM solution that we provided with one of our customers. And then I'll go through next steps and how can we help, and then do a question and answer session at the end. Pedro, if you want to take it off.
Awesome. Thank you, Danny. So like Danny said, the first thing is, what is asset performance management, or APM? APM is a holistic approach that combines technology, data, and strategy to maximize the reliability, availability, performance of any physical asset across a facility. So at its core, APM is not just about, fixing machines when they break. It's about ensuring that every asset on your line, whether it's a pump, a labeling machine, or any piece of equipment, operates at its, full potential all the time, with minimal unplanned downtime. APM solutions use real-time data and analytics and visualization to help our engineers and plant managers to do the following things. The first is to predict failures before they happen. It helps you optimize maintenance schedules based on actual usage of the equipment. It also improves equipment efficiency metrics like OEE, for example. And lastly, it drives better decisions using historical and live data. It also shifts operations from a reactive mode, like we fix machines only when it breaks, to a more proactive and even predictive mode. So we address the root cause before performance drops, right? What makes APM really powerful is that it connects the dots between operations, maintenance, and production. It brings these traditionally siloed areas together into one unified view of performance. That enables both the frontline operators and your senior engineers to work from the same set of facts and in real time. So now that we've defined what APM is, let's break down the key capabilities that make it such a powerful tool. The first is real-time visibility. So APM systems continuously track what's happening on your lines. Whether a piece of equipment is running, it is idling, it is faulted. This will be monitored, and this allows operators and supervisors to respond to these events immediately. So if your equipment enters a fault state during a shift, the system could instantly highlight that in the UI or even trigger an alert, right? The second is automated data capture. So there's no more whiteboards, clipboards, no more manual shift logbooks, no giant Excel sheets. Every state transition, every count, or any event in your facility is captured directly, either from PLCs, sensors. So there's no human input required. That means that your line performance, your production counts, your downtime events are all stored in a database, and they're ready for analysis every time, accurately and consistently. The third is turning that data into actionable intelligence, right? So it's not just raw data, but insights that tell you why you're losing performance. So for example, if performance is your lowest OEE component, you'd be able to drill down to see that one of your equipment in your line is causing frequent stops during the day, which allows operators to, respond accordingly. And lastly, APM is scalable. So whether you oversee one line or 50 lines globally, these systems give you remote access to real-time and historical performance data, and without you having to install custom infrastructure at every site. So that means your corporate engineering team and your local maintenance crew can work from the same real-time insights. Now that we've seen what APM is and what it does, I want to talk about why it actually matters, right? Especially in the environments that many of you work in. The first one is that paper and spreadsheets fall short. Many plants are still tracking downtime, throughput, or even OEE in Excel or worse on paper, which introduces delays, inconsistencies, and zero context, right? You might know one of your lines went down, but not when, why, or even for how long it went down. And these methods were introduced a long time ago for documentation purposes, and they're not really good for decision making. And when you're trying to optimize a process, this is one of the major limitations. Second is the cost of the delay data. So when data lives in someone's notebook or logbook, or it gets uploaded 2 shifts later, it's already too late and the issue has already passed, and you're reacting instead of improving. So APM gives you real-time awareness, so you can act on issues before they impact production for the day or for the week or even for the current shift. Another reason why why it matters. And it's one of the common challenges in operations that we hear from engineers and plant managers all the time is it helps you understand inconsistent uptimes. So like no one knows exactly why the same line performs better one day versus the next. And APM can help you pinpoint those as well as show you blind spots in your OEE. So if you get a score, but you can't tell if it's the availability, performance, quality, what is driving the loss, it helps you show you that. And lastly, it's that reactive maintenance, right? So if equipment fails and only when that equipment fails, we find out the signs were already there hours ago, but you weren't able to react on time. So APM addresses these head on by creating visibility, consistency, and a shared truth. So now that we've looked at APM and explain why it matters and all of its capabilities, I want to show you a live demonstration of an APM application that we developed in Ignition Perspective. This system is built around a fictional brewing packaging plant located in Portsmouth, Massachusetts, and it's designed to represent the kind of real-world operations you'd see in a fast-paced production facility. So let me pull it up. So what you're seeing here is the overview dashboard of Tech Hops Brewery. At the top, we have two production. You can see we have two production lines. We have the bottle line and the keg line, and these facilities. This facility handles both packaging formats simultaneously, and right away we get a sense of how the lines have been performing over the last hour. The pie charts at the top show the distribution of the equipment states. So how much time was spent running, how much time the equipment was blocked, how much time was lost to unplanned downtime, or even how much time the equipment was starved. And below that line, below this pie chart, we get a line chart that shows the actual production counts versus the target counts for the past 24 hours. And these targets are automatically calculated based on each line's standard rate. So if we're falling short, like we are doing right now, it usually means that there's an issue with how the equipment is running. So let's investigate that, and let's drill into the bottle line by clicking on its state pie chart. And this will bring us into the bottom line. So what we're seeing here is essentially an and-on board for this line. It provides a full breakdown of the bottom line, which each individual cell in the process represented. We've got a cleaner, a filler, a capper, a case packer, and a palletizer. And each one of these is color-coded based on their current real-time state, which could be either running, blocked, starved, in unplanned downtime, or etc. In the top left corner here, we have a set of state KPIs that summarize how the entire line has performed across 3 time windows: the last hour, the current shift, and the entirety of the day. And for each period, you can immediately see how much the line has spent running in planned downtime and in unplanned downtime. So for example, in between the sum of all of these 5 cells, we've ran 192 minutes in the last hour, which isn't great because we have 5 cells. So if we were running all the time, this would be 300 minutes, right? So we immediately know that something's going on in our line. And this is huge for shift supervisors and engineers because it takes what would normally be buried in logs or in a database and just exposes it clearly here in real time. Right below those KPIs in the bottom left corner, we also see a dedicated widget here for OEE metrics at the line level. So you're getting real-time availability, performance, and quality percentages, not for a single machine, but this is for the entire line. So this helps you understand whether the biggest losses are due, again, to stop time, slowdowns, or any quality rejections, and would allow your team to prioritize where to focus. This level of analysis also gives you like a middle layer of visibility between the high level plant view and the individual asset level, so you can take action at the right level of detail. What is also really nice about this screen, and one of my favorite parts, is that it's more than just a status screen. These states respond to one another. So you might have noticed that while I've been talking, but for instance, if the capper were to go down, the filler and the cleaner upstream would eventually get blocked. And if the downstream case packer isn't receiving product, then it becomes starved. This will give you a real-time cause and effect view of how equipment states cascade through the line, and something that's like really hard to visualize without a system like this, which is really nice. Now, if we want to go even deeper, we can click into any one of these cells. So let's open the capper, for example, and we get a detailed view of this asset. So here we can see how much time it spent running during the last hour, the current shift, and the entire day. We can also view the production counts for this specific cell, which let us compare the actual throughput against what we would expect at standard rate of this specific cell. And lastly, there's also a clear breakdown of OEE metrics for this specific asset. So we got its availability, its performance, and its quality, which is, again, incredibly helpful when diagnosing which specific cell is causing the issue in your line. So like what makes this interface really powerful is that we started from a high level overview, and we were able to dig down into a granular diagnosis within seconds. So you can quickly spot something's wrong from the top level dashboard. Maybe one of your lines is showing a lot of unplanned downtime, and then you can drill all the way down to the specific machine, identify its recent history, and respond accordingly. Lastly, what I want to show you is if we jump into the keg line here, you'll see that it's a very similar layout. This line is just simpler. It's just a cleaner with a filler, but it follows the same structure. You can dig deeper into each one of the cells if you want. But this standardization is intentional. If we were to add another line or even deploy this across a different facility entirely, this system is built to scale. So you could create a corporate level overview, for example, that monitors multiple packaging facilities, let's say. So say you have facility A and facility B, and then you can drill down into any one of these lines or machines using the same logic and interface. So there's consistent visibility, consistent action, and just a faster response no matter where the problem shows up. So yeah, this is the power of a well-implemented APM system. It gives you the real-time awareness. It helps you detect and respond to issues before they escalate. And it gives both engineers and operators the ability to visualize performance trends and just act on them. All of this adds up to better reliability, better throughput, and ultimately a better business performance, which is what we're looking for. I'm now going to kick it off to Chris so that he can share some real-life case studies of where NeoMatrix has implemented APM systems. Chris, get it off.
Thank you, Pedro. Next slide. I'm going to talk about an APM system we deployed over the last few years at an electric vehicle manufacturer. There were pretty much 5 stages involved in this process. One of them was developing the production model. That's a description of all the assets in the enterprise. It's based on ISA 95. Second is gathering data from the PLCs. Like Pedro was talking about, you don't want to have to be entering data manually. You want to get as much data as you can out of the PLC or any control system automatically. Then we built a system to record state, mode, and count changes in a database. This would then allow us to do analysis long-term. A lot of the metrics for last hour, last shift, last day that Pedro was showing based on database information. It's not data that's being continually incremented in some type of counter in the PLC or that. It's all database based. Fourth was to build dashboards for the manufacturing floor, similar to what Pedro showed. And finally was building additional analysis tools for engineers to be able to look at larger periods of time than were being displayed on the dashboard. The dashboard is usually limited to is a real-time tool that displays the current day. This analysis tool allows us to go yesterday, last week, last month to understand what's going on. So the first one was building the production model. It's good if it's aligned with their MRP, ERP system configuration, but that rarely happens because we go a lot deeper than an ERP system usually goes with their layout of their definition of the production facility. So if in fact for shops like General Assembly, we started at the shop General Assembly, went down to the lines, the stations, and down even the operator stations on each side of each cell to get as much detail as possible. Second step was develop an AOI to collect state being the state of the equipment, counts in when a job is started, as in when a vehicle enters a workstation, count out when a vehicle or part leaves a workstation, that's good. And then reject counts would be when a vehicle or other part subassembly leaves the station, then there's a defect. All of this was done, the vast majority of the PLCs at this site were Allen Bradley. So we built an AOI that was dropped into all the control PLCs, plugged into their state machine, and we got the information we need, but the current state as well as a rolling count of the ins and the outs of the bads. So the third step was then once we have that data, we have the source for that data is to collect the data in Ignition, through Ignition into a database. So we developed a UDT that was designed to record changes as they occurred and store those changes in a database. For you to get a little weeds, for you Ignition nerds, we were using tag change events, which can be problematic if you have a lot of the events happening at the same time. So to deal with that scalability issue, we use a Java in-memory queue, and the change event basically just pushes the information that is needed to insert into the database onto this queue, including the time of the event, of the state change or of the count. And then we have a separate thread running that takes that data and actually sticks it into the database. That drastically improved our performance. All of our timestamps are within milliseconds of the actual event. So we're real happy with the performance of this. We're also built the stored procedure in such a way that we don't record very small event changes. So if you go from starve to planned downtime to running, and that planned downtime maybe lasted a second and a half, there's no real value to that because it's probably noise with the way the AOI has been wired in the PLC. So we'll just ignore real short durations so we have real usable data. So next slide, thank you. So the other key number, or the key parameter is mode. Mode is the intended use of the asset. State is what actually is happening. So mode would be things like in production, on break, at lunch, plant closed because it's 2 in the morning and we don't run at 2 in the morning. So to do that, what we built a scheduling system for them where they could set the schedule for the site, the area, and the site, the shop, and line and sublines even for as a standard one, and then be able to override as needed. So for example, you'd set the lines in General Assembly to run from, let's say, 6 a.m. to 4 p.m. with a couple breaks and lunch in there. But then when you had a holiday, you could then just set the holiday for the entire enterprise, and it would roll down and trump the standard schedule for any line or subline. So also that can be edited after the fact. So in essence, it acts as a mask over the raw data so that we can exclude anything that's happening at lunch or at 2 in the morning. If for some reason maintenance is working on it at second, when the plant is down, we don't want that data to influence our metrics. So after that, after we have the data being stored in a database and being collected, we're going to build dashboards, and the dashboards are going to include things like Pedro showed before, cell states, line counts, cumulative production targets and variances against those, critical alarms. In some cases, we put in trending graphs. If we go to the next slide, you'll see an example of one of the billboards we made. In this case, this is a subsection of a module line in the powertrain area. So we have both current hour actual and accumulated target counts. The accumulated target will increment over the hour based on the standard rate, as well as for the day, the actual versus target, and then we know what we're trying to make for the entire day. So you can see that for the last hour, we're under target, but we are well ahead of our target for the day. Below that, you go back. Below that are the states of the cells. This is at a top level. There's a lot going on. So under bucket marriage, that would be a group of cells. And under that are three different distinct processes that run in parallel. And there's actually a lot of processes even under that. So this is more of a top level of a cell group. 070-201 is faulted, so we know that there's a problem there. And then we use logic to determine, since these are parallel, what is the actual state we want to display on the line above it. In this case, we've decided that, well, if one's faulted, one's running, and one's overcycle, we're going to show that the group of those three is overcycle. Same with the cooling plate and so on. And this can be tailored to whatever the organization needs. Some people want to see all the cells. Some people want to just see the top level. It all depends on what their needs are. Okay, next. So finally, what we did, we build analysis tools. We had this database of state durations and counts, good counts and bad counts. And what we could do is build tools to analyze that. You know, for example, like Pedro had in the demo, show me the breakdown percentage-wise of all the states for a specific time period for a specific machine. Same, calculate the OEEs for that same time period and machine. Look at the cycle time. Look at the cycle times for all the way down to the individual serial numbers of parts that are going through the lines, and look at, you know, what is our average cycle time? What's our maximum cycle time? Was there a problem with one part continuously throughout the line? That kind of stuff. All that information you can get with these analysis tools. Besides looking and finally looking at production counts so that you could see when parts were made, including the serial numbers for those parts, and get a distribution by hour. So that's pretty much it.
Oh, Danny, you're muted.
Oh, thank you. Yeah, so next steps, if you want to go to the next slide. So at the heart of asset performance management, it's really to drive higher availability, throughput, and quality in your capabilities, ultimately leading to better profitability. And by implementing this solution, you are really taking the first step in understanding what you can do to improve your manufacturing capabilities, to ultimately decrease your cost and increase profits. We can help you to assess where you are today and help provide a readiness plan for your plant. So feel free to reach out to me on that, and we can take a staged approach really to help you to prove an ROI on that initial investment. So I guess we could turn it over to questions and answers. If people want to write in any questions that you may have. What's an AOI, Chris? Just in, oh, you're muted.
Thank you. It's an add-on instruction. It's a piece of code you put in the PLC that is, excuse me, sort of like a subroutine in other programming languages. So you can drop multiple instances of the same logic in different rungs in your PLC code so that it does the same thing in multiple places independently.
Well, as Kristen mentioned in the chat, we will be sending out a link after the webinar, and we will also be posting this webinar on our YouTube channel. We do have
I can answer Sherry's question. So what's secondary? excuse me, what secondary root cause analysis have you been involved with or witnessed in your use cases? Excuse me 1 second. Okay, so when we talked about states, there are 7 types of states. The most important being running, planned downtime, unplanned downtime, starved, blocked, and idle, and I always forget the 7th. So from a fault
Disabled.
standpoint, what's that?
Disabled.
Thank you. Idle and disabled in my mind are basically the same thing. So from a fault analysis standpoint, we found that by creating a state, an integer that represents that state for each specific fault that we want to track, we then record that specific fault. From an OEE standpoint, all of those specific faults have the type of unplanned downtime, so we still can calculate our OEE, we can still show it as a color of red when it's faulted, but then we can have analysis tools to go, hey, show me these states and give me an analysis of all the faults, what's the most prevalent fault? So you just do now, basically you're doing state analysis on a subset of states.
Do you show that in terms of a trend?
You can show a trend, you can show on a bar chart or a pie chart. You can do whatever you want with it. It's state analysis for, like I said, a subset. We're waiting because we're seeing people type. So Sherry follow up. Okay, great, thanks. But how do you get to corrective actions for the fault types unless you know, for example, it is mechanical, electrical, wireless, etc. So that comes in designing the states and designing the logic in the PLC to create those specific states. You can also go back after the fact and set up a system where you could put a description for a specific state period. We do that in some of the lines at the EV manufacturer for if they're overcycled for a specific car, they'll put in a note as to why they were overcycled. So you can use that as well. But the problem with that is that you're going to add that extra data. So as much of it as you can do automatically, you're going to get better data. And Mike C writes, what has been the time to assimilation in regards to end user adoption, technician and manager fluidity, as well as value identification when the client sees the value of the adoption? First, I like the Star Trek Next Gen reference about assimilation. It all depends on the leadership. We were lucky. The manager, the directors of the various shops saw the value, so they pushed to have this information. Once you have all these TVs around the shop with the states going on, what's going on, counts, everyone sort of buys into this. Oh, that's my metric. Oh, I can see what's going on with the rest of my line. It really was not that difficult. Again, though, it comes from the top. Is like if senior management wants it, put it out there, and then people see the value of what it is. If they don't see the value at the top, it's not going to work.
I would add to that is a key piece of that is the return on investment, right? So if it's data that's going to allow you to fix something to improve throughput, for example, where you can generate more revenue for the given cost of an equipment, your margin goes up. And I think there the management and the leadership team should see the value of installing something like that due to the increased profits.
Gary asks, can you create a simplified dashboard for the production floor that lets frontline leadership identify a problem and react quickly to correct the problem? Absolutely. One of the dashboards that I think a supervisor came up with at the EV manufacturer was an overall status board that showed the state of, in auto manufacturing, you basically have trim, powertrain, trim, trim, it's the second line. Three main lines that the equipment goes through. And then there are a lot of sub-assembly lines, like powertrain, be the front and the rears. There'll be a front end assembly, sub-assembly line. All the various sub-assembly lines as well will all be displayed in one dashboard, so you can see where your problems are. You can see, do I have, because everything is serial number matched, so that we know that the last part coming out of the front assembly sub-assembly line is going to match this specific car. So you can see where there might be problems, because auto manufacturing is very big into buffers. That's basically work in process between various cells. So you can see how many sub-assemblies are between the sub-assembly line and the main line to understand, okay, I'm going to have a problem soon. I got to figure out what's going on the subframe line or something like that. And the three shot, I now remember the lines, the three trim, where they put a lot of the material on the inside and take the doors off, because the parts on the inside of the door are entered on the door line. So at the beginning, they take the doors off, they send it to the door line. Then the car goes through chassis, where a lot of the powertrain in regular car manufacturings, there would be axle, engine, transmission, and an EV be the front and the rear assemblies goes through. And then there's the final line where they finish adding stuff, put the doors back on, make sure all the gaps between all the panels are good, polish it up, and then send it out to end of line. But to answer, you can, because you have all this data, you can create almost anything you want to create.
Danny, I think you're on mute again.
Yeah, thank you. Yeah, I was just wanted to thank everybody for attending today. Appreciate your time in attending, and appreciate all the questions that you have. If you do have any further questions, feel free to reach out to me at any time. There'll be a follow-up email by Kristen that will kind of give you all the resources, as well as my email for contacting me in the future. And have a great rest of your day.
Thank you.
Thank you.